Hey everyone, in my last video I showed you this raw, unpopulated PCB that I had made for my electrical power system, or EPS, for my $1,000 CubeSat. I have finally had the time to actually populate this board with real components, and I'm happy to report that most of the design works. There are a couple of issues with it, and that's what I plan on covering today. First things first, at a high level, everything pretty much works. Power from either the solar cells, an external USB, or from the batteries themselves flow through the battery management chips, through the ideal diode, into the 3.3 volt regulator and the 5.0 regulator, into the load switches, and then it also powers the power management IC. I've also been able to write code and flash to this STM32 microcontroller, or PMIC power management IC. So you can see that in action. If I actually supply power to this board, you can see that some LEDs start to blink, indicating that at least some basic code works. I'll be going over the software hierarchy in another video shortly, with a whole bunch more details there. So let's go into the solar power and battery management section of this schematic. I have been able to verify that the battery management chips, the battery chargers, do actually charge a battery, either from an external power source, which is this USB chip, or this USB plug, or from an external solar source. So I've put together these little solar cells, which are the same ones that I've shown in a previous video, and using these as the source, I've actually been able to charge this battery, although I haven't had very good light conditions, so I've only been able to use a 1600 lumen light bulb placed literally directly on top of these to actually get a charge. It was around 100 milliwatts of power that these panels were outputting, which is far less than what they could output. I just haven't had a sunny day in a while to actually truly test these. When solar or an external power source is removed, the battery charging chips seamlessly transition from using either the external power source or the battery as its main supply. So it's working exactly as I thought it should. I can remove the source and the microcontroller stays on, no problem at all, as it switches to using the battery as its power source. These are the battery chips themselves, these guys right here, and they were quite a pain to install. They are QFN packages, and I've never done those before, so I'm honestly surprised I was able to install both of them, and everything seems to be connected and everything seems to be working just as advertised in the datasheet without actually breaking either of these chips. On the underside, you can see that I have the exposed pads on the bottom, and I think I had what made these so difficult to install was that I had 5 through holes, and all those through holes have solid connections to the ground plane, so these were quite difficult to do with hot air. So I had to use hot air and a soldering iron underneath it just to get them to solder onto the board. All the vias on this board use solid connections instead of thermal spokes, which in theory is nice, but it makes installing some stuff by hand quite difficult. Another thing I found while testing out these solar cells is that this design really does not support low light ambient conditions at all. I'm confident that this design will work in higher light, higher sunlight conditions, but in terms of just harvesting energy from a room, this design just does not cut it. These battery charger chips want to draw too much power, more power than in low light conditions than what this maximum power point tracking chip can supply. And if that's the case, then nothing happens because the input voltage is just too low. There might be a way I can work around this low light condition. So for the battery charger chip itself, so this is the schematic for this block here, there are 2 things I can control. There is a shutdown, or it's a suspend. One of those will just stop any input current. So this might work in the case where I want to disable one of these battery chargers and leave the other one to charge. The other thing I can do is there's this high power input. Pulling this low will limit the input to 20% of whatever I've set it to, which might be useful to allow it to work in low power or low light conditions. By default right now I have it pulled high. I don't even have a way of I have not connected it to the microcontroller to give it the option to pull it low, but that's something that I could do in a future revision. I also noticed some interesting behavior with this power good output from this maximum power point tracker. In the case where these solar cells weren't receiving a lot of light, this maximum power point tracker wouldn't necessarily reach 5 volts right away. And what I would notice is that if V out was somewhere around, say, if this is 5 volts, it'd be somewhere around 3 volts. And power good didn't seem to have much of a trigger on it, so it actually, the voltage on it kind of sloped upward. I was hoping to see something that looked more like this, where it's clearly down at 0 volts and then it jumps up to 5 volts right as the power is good. However, that's not the case, and the reason that this is an issue is that this load switch also doesn't have a Schmidt trigger input, and it partially turns on with these intermediary voltages. Now, this isn't much of an issue when I have a lot of solar light or a lot of input, because this maximum power point tracker can then output 5 volts with no issue because it has a lot of power to draw from. However, when it's outputting something like 3 or 4 volts and then this load switch is actually passing it on to the battery chargers, it's preventing this maximum power point tracker from actually getting up to 5 volts because that intermediary 3 to 4 volts is actually being consumed by these battery chargers but not doing anything useful, and it's just dragging down this maximum power point tracker. So it would be useful to input a Schmidt trigger or something right in here to actually have a clean turn on and turn off of this load switch, just so there isn't wasted power, and then that the power that is received by these battery chargers is actually can actually be used for something, because these require 5 volt inputs. So moving down the line here, let's take a look at the battery heater control circuit. So first thing, and you've probably seen these hanging around, these are the thermistors that I use. These are a part of the battery management chip. They require these thermistors in order to monitor the temperature of these batteries. They're not actually hooked up right now. I just assume that the battery is fine. But in practice, these would be attached thermally to the battery in order to read if it's too hot or if it's too cold. Specifically, the circuit that we care about is this one, and this is what feeds back right into the battery charger chip itself. So VNTC is something that the battery charger chip outputs. It's roughly 5 volts. NTC is its feedback, and this is a 10K resistor, and then this is the thermistor itself. So I was able to test with some ice cubes and a lighter, and I could see that, yep, charging stops if I freeze it or if I get it too hot, and that's great. However, using this VNTC signal and this NTC signal, I actually feed those back into my own circuit using a comparator and a load switch in order to use it as a heater for the battery in case it gets too cold, because charging a lithium-ion battery that's freezing can actually damage it. Discharging it, I believe, is okay though. What I came to learn about this battery management chip is that the VNTC signal, or this bias signal, and this is not 4 volts but 5, this VNTC signal is only actually present whenever the battery chip is charging. So that means if an external power source is connected or if there's solar energy, that is the only case when VNTC is present, which means I had made the assumption that VNTC was always on and that I could always heat the battery. This isn't a big deal because the battery only needs to be heated if it's being charged, because that's the damaging condition. However, I just didn't anticipate that, so there might be some weird behavior if VNTC is 0. I might end up accidentally, depending on what, because this is 0 and then this would also be 0. The state of this comparator I don't quite know, and it might vary from comparator to comparator, so it might end up heating the battery even when it shouldn't, or something along those lines. Also, the bigger issue with this circuit is that I flipped the inputs of this comparator. So NTC should feed into here, and this VNTC divider should feed into the negative input. So what it does is the opposite of what it should. It heats the battery when it's at room temperature and stops heating it if it's freezing. Oops. So moving on from the battery into the next part of the schematic, which is the ideal diode. So each of the batteries output into this ideal diode chip, and there's one ideal diode from VN to VOut, or VN2 to VOut2, and VN1 to VOut1. I end up connecting these together, which form the voltage bus for the rest of the system. What's interesting about this chip, though, is that each of the enables, one of them is active high, one of them is active low. To turn on VN to VOut, you have to pull EN2 low, and to turn on VN to VOut1, you have to pull EN1 high. That's fine. So I pull ideal EN2 low, and that's done. That's done down here with a 100K pull down, and ideal EN1 is pulled up to 3.3 volt EPS STM. Now, that's an issue with this pull up because 3.3 volt EPS STM is only created after the ideal diode itself is turned on. So we have a bit of a deadlock here. You can't have ideal EN1 pulled up unless you have it already on, so it doesn't really work. Ideal EN1 needs to be pulled up to probably just VN1 because that's, I think, the only way that it would properly work. And you can see that in action here. So let me disconnect the external power. Well, first of all, the battery chips and the ideal diode work just fine if I have 2 batteries installed, that's fine. And I can actually remove one of them, and that's fine. However, let's see, the issue is this is battery 1 that has the issue, and battery 1 is this one. So I can install, let's plug this into battery 2's slot, and then the lights will come on for the microcontroller and everything seems to work just fine. However, if I install this into battery slot 1, nothing happens. Nothing happens at all because ideal EN1 is not pulled up. But if I connect the external power and then remove the external power, things work fine. So that's a simple little resistor change that I need to do to make this circuit work as I thought it should. And the last thing for the solar power and battery management system that I've found wrong is that these batteries are too close together. So the widest parts of the batteries don't touch. However, these little tabs at the top of the battery clips do touch. So if I install the other one, they do fit together. The grounds touch, and that's fine because the grounds are already connected on the board. However, the positive sides should not touch. They're not designed to touch, but they do. So I had to solve that with a little bit of tape here. So next design will have these moved a couple of millimeters farther apart, and that should do it. Now let's talk about the PMIC Power Management IC. So really only one thing wrong here. So here's the chip itself, and you can see this white wire running off of it. So this is for the BOOT0 pin. So that pin is designed to select if you boot into the chip's bootloader or if you boot into its regular programmed flash memory. And I had it floating, so it would either boot into its bootloader, which it expects some external inputs in order to actually do something, or what I wanted it to do is boot into its flash, where it would actually run the program that I flashed onto it. So I had to tie this signal low, and this was the most convenient ground I could tie it to. But it's a pretty simple fix. I just add a resistor pull down onto this pin, and that solves that. You might notice that I have not populated the CAN transceiver or the MRAM chip, and I figure that these are more software problems, and I didn't want to spend a whole bunch of time trying to bring these up just for this video. I'm assuming that they will work, but I mean, of course, I haven't tried them out yet. I will be trying them out in the future, but I figured that these are mostly just a software configuration problem more than anything. Now let's talk about the current monitors and load switches. And that's what takes up most of the space on this board. So these are all current monitors and load switches. There's 16 of them. A whole bunch here that I have not populated, and that's for good reason. One, I really set myself up for a whole bunch of work populating everything here. And I do plan on populating at least the load switch part, but the current monitor, that's something that actually has a couple of issues. So here we are on the current monitor page, and the first issue is actually a parts list issue, or the first two issues are. So I have these 2N700 2K NMOS transistors, and I use these 1 mega ohm pull-up resistors in their operation. Since the 2N702 is like a super common, just standard garden variety transistor, there are of course a whole bunch of different varieties, all made by different manufacturers, all with a slightly different specs. So I purchased the 2N700 2K, specifically the K variant, for this project. And what I came to realize is that I couldn't use 1 mega ohm resistors with it. And that's because this is the gate and this is the source. The gate to source leakage current was plus minus 10 microamps, which sounds pretty small, but because this circuit operates at 3.3 volts, this is 3.3 volts and this is 1 mega ohm, I only have like 3 to 4 microamps coming through these resistors. And so what ends up being the outcome of that is, since here to here requires at most 10 microamps, and this is only supplying 3.3 microamps, there's actually, this pull-up doesn't actually work. Ends up being just a weird voltage divider, such that it ranges from 0 volts up to not 3.3, but rather 2 volts or 1.8 volts, something around there. Anyway, this just caused some weirdness with whether this transistor would actually be on or off, which affected this transistor as well, and this also has a 1 mega ohm pull-up, which then affected the output. So the solution is to either bump these down to 100K ohm resistors, which is fine, or there's another packet, like the exact same package from the same manufacturer, but it doesn't have the K. It's just the 2N702, which is rated for 10 nanoamps of gate to source leakage, and that's what I wanted. So this is another reminder to read your data sheets, because small little things like that will get you. The next partless problem I found was that this amplifier, I intended on using the NCS211, but inside KiCad itself, the field I had for this part was the NCS214, which this has 100 gain, this is rated at 100 gain. The NCS211 has a gain of 500, which that's what I wanted, and that's what I sized these resistors for, and that's what I sized the shunt resistor for. And that's where I came up with this equation where I rely on the gain to come up with all the numbers. So this just resulted in having to change some resistor values, which is fine, but really it's just another thing where I just needed to buy the correct part and everything would have worked as I thought it should without having to recalculate stuff. The next issue, and the most difficult to fix, was this comparator. I again flipped the polarity of the inputs. So this is the same part I used on the battery heater page, and I wanted to use the same part for part commonality because that's nice to do, but I also flipped the polarity. So instead of disabling a high current event, it will allow a high current event, except it will also disable a normal amount of current event. So essentially it's useless as is, and this needs to be connected over here, this needs to be connected down here, and then these traces need to be cut. So essentially it just needs to be totally flipped, which is fine and can be easily done in another revision of this board, but it is certainly a pain to do after the fact. Another issue with this design is this capacitor and this capacitor, as they are right now, do nothing. I included them with the intention of having a low-pass filter on either the output of this amplifier or on the input of this amplifier. But as they are right now, they don't do anything. And that's because a proper low-pass filter on a differential input doesn't look like this. You need to have resistors, and a proper low-pass filter on the output needs to have resistors as well. So this either does very little or nothing altogether, and same with this. So what it ends up needing to look like is, if this is the positive and negative input, you have a resistor here, and then you have your capacitor, and then it goes into the input of the differential amplifier. For the low-pass filter on the output of this amplifier, you need to have a resistor right here, and then have your capacitor here as well. So that's something that I needed to put in because I ended up realizing that I do want to have a low-pass filter on the output. I could have it on the input, but it seems like you need to have a bit higher tolerance on these parts, and the simpler, fewer part solution is to just have it on the output, and I think it'll be good enough for what I'm trying to do. You can see this nasty rework where I had to cut some traces and white wire some stuff around to actually get it to work. So that's why I haven't populated everything else, because I would have had to do this to actually make the circuit work. And the reason I need this low-pass filter is because when I turn on the load switch, it turns on very quickly, and that results in a little bit of a current spike that goes through here. That current spike is picked up by the amplifier and the comparator. So what happens is this turns on, load switch turns on, and then the amplifier immediately detects that there's a current spike. The comparator, once this is fixed, of course, turns off. So it turns back off the load switch, and then after this monostable pull down, it expires. Then this turns back on, there's another current spike, and the cycle continues. So essentially I just built a way complicated oscillator for the load switch, and of course that won't work at all. This is solved by having a low pass filter here. However, it's a bit tricky because having a low pass filter here, essentially, I mean, the whole point of this current monitor circuit isn't just to kill it if it goes over, X amount of amps. It's to quickly respond to a single event upset or single event latch up specifically, where solar radiation latches up a transistor, causing it to pull excess amount of current. So it's tricky having to size this properly, where I want this circuit to respond quickly to any sort of overcurrent events. However, I don't want it to unnecessarily shut off a circuit, because in normal operations there are little blips as the circuit is used. So it's tricky having to size this properly, to size this low pass filter, sizing these resistors that the comparator uses. And in some situations, the more I think about it, the more it makes sense to probably have some sort of digital circuit that the power management IC actually controls, because for some parts I think this analog solution works perfectly fine. But for other parts, like a microcontroller, the amount of power that a microcontroller can use can vary widely, from tens of milliamps to ones of milliamps. And there really isn't a single good constant value that works for all of that. So that might be something I end up changing about a future iteration. So those are the issues that I've identified so far with this board. I don't think I'll make another revision of this board just yet. I think I'm going to hold off until I find out if there's anything else that's wrong with it. But also, this is a perfectly fine development board as is. I mean, the microcontroller works, which I was hoping it would. All the power stuff pretty much works just fine. The current monitor might be broken, but I don't need the current monitor to be able to turn on and off power rails. I don't really expect single event upsets to happen here down on Earth. So for now, I'm just going to keep it as is. The next board I plan on making would be the avionics board. The last thing that I wanted to mention, and another reason why I'm holding off on doing another redesign of this, is that this board, as is, by no means meets the requirements that launch providers expect from CubeSats. And that's not to say that anything is specifically bad or wrong about what I've designed here. It's just that I'm missing specific electrical inhibits that you'll see on every other CubeSat. I'm referring to the CubeSat design specifications found at CubeSat.org. This is the spec that I really ought to design against, since I'm not aware of any other spec that's out there, or at least something that's as well written and organized as this. And if I have any hope of launching this CubeSat, I ought to design against that. I'm sure I'll make another video going into the design specification in more detail and what I need to do to actually meet that spec. But I'm definitely going to hold off on making another revision of this board because I am completely lacking the remove before flight pin and the deployment switch, both of which focus mostly on the electrical power system, so I would need to somehow figure out a way of incorporating them into here while meeting all the specs. And I took a quick glance at the document, and I know I don't meet those, and it would require a bit of thinking in order to meet those, so I've decided to just ignore that for now as something that I can probably just end up doing later, because really what I need to just focus on is getting this design working first, and I'm sure that I can add some switches or something or some inhibits into this design later. Anyway, that is all I have for now. Thanks for watching, and Happy New Year!